A tunnel boring machine is a specialized excavating machine used to precisely build circular tunnels. A TBM is essentially a long train of interconnected systems, despite the fact that many people think of it as a single enormous drill. Only the excavation is done by the spinning cutter head at the front. Behind it are dozens of other sections that house operators, provide energy, manage navigation, install concrete tube segments, carry excavated material, supply hydraulic power, and circulate cooling water. So how does this giant machine cut through solid ground without the earth above it collapsing? How does it know where it is going? And how can it construct an entire subway tunnel under the ground? Let's look inside one of the most impressive engineering machines ever built. The machine's most identifiable part, the cutter head, is located at the very front. The cutter head is a huge revolving steel wheel that can have a diameter of over 15 meters. Dozens or perhaps hundreds of specialized cutting tools, chosen especially for the local geology, cover its surface. These are typically disc cutters in hard rock. Each hardened steel disc applies tremendous pressure to the rock, rather than cutting through it like a drill bit. The rock cracks and fractures into smaller pieces due to the focused tension created by the discs as the cutter head revolves. The cutter head scoops material into apertures close to its center using cutting knives, scrapers, and buckets for softer terrain like clay, sand, or gravel. The forces involved are enormous, despite the cutter head appearing to move slowly, usually about 1 to 3 revolutions per minute. Thousands of tons of thrust are produced by hydraulic cylinders behind the machine, which firmly press the cutter head against the tunnel face, while strong electric motors supply the torque required to keep it spinning. The excavated material, referred to as spoil, does not just fall into an empty tunnel when the cutter head breaks apart the rock or dirt. Rather, it goes straight behind the cutter head into a meticulously regulated collection chamber. A massive screw conveyor, sometimes known as an auger, is located at the bottom of this chamber. Material is gradually drawn from the pressure chamber and moved toward the back of the machine as the screw revolves. This conveyor speed is precisely regulated. Pressure at the tunnel face may decrease if it rotates too quickly, raising the possibility of sinkholes or ground settlement above. Turning too slowly causes pressure to build up inside the chamber, which puts undue strain on the machine and slows down excavation. Conveyor belts take over once the spoil exits the excavation room. Every hour, hundreds of tons of excavated material are transported by these nearly non-stop systems back toward the launch shaft, where it is loaded into trucks for recycling or disposal. The cutter head has started digging the next tunnel segment by the time the spoil comes to the surface. However, the machine must first produce something robust enough to sustain the massive weight of the ground above before it can proceed. A tunnel boring machine's ability to simultaneously build and dig a tunnel is one of its most amazing capabilities. The erector section is located directly behind the excavation chamber. Here, a permanent, structurally reinforced subway tunnel is created from the unfinished excavation. Modern subway tunnels are usually constructed with prefabricated concrete segments instead of pouring concrete beneath. The proportions of these enormous curved pieces can be precisely regulated to within a few millimeters, and they are produced in specialist facilities. Rail trucks or specialized supply trains deliver each segment, which weighs several tons underground. An automated hydraulic arm known as the segment erector starts building the subsequent tunnel ring as excavation stops after each advance. Each concrete segment is lifted separately by the erector, which then carefully positions it against the ring that has already been erected after rotating it into the proper orientation. People or automated systems fasten adjacent segments together with high-strength bolts. The majority of tunnel rings are made up of 5 to 8 separate segments, in addition to a smaller last part called the key segment. Installing the key segment comes last. Despite frequently appearing to be the tiniest component, it serves one of the most crucial purposes. After it is placed, the entire ring is locked together, enabling the separate segments to function as a single, continuous structural unit that can sustain thousands of tons of surrounding ground. Steering and navigation have to be very precise. Just a few degrees difference can ruin the whole project. The solution includes gyroscopes, laser navigation, accurate surveying, and computer control systems. Surveyors carefully map out the exact path of the tunnel before any digging begins. Every curve, every slope, every elevation is calculated before the machine is built. A strong laser is mounted behind the machine after the launch shaft is finished. This beam acts as a permanent reference line that points exactly along the intended tunnel alignment, in contrast to a construction laser used to level floors. An optical target inside the TBM continuously tracks this laser's location. The machine determines that the laser is perfectly aligned with the planned route as long as it hits the target center. Of course, not every issue can be resolved by lasers alone. Optical measurements may be hampered by dust, moisture, vibration, and the tunnel's length. For this reason, inertial navigation systems are also used by contemporary tunnel boring machines. These devices have extremely sensitive accelerometers and gyroscopes that continuously detect even the tiniest shifts in direction and movement. From a computerized control room situated several sections behind the cutter head, operators keep an eye on all of this data. The machine's onboard guidance computer determines the precise amount of adjustment required each time it starts to enter one of these curves. The tunnel boring machine modifies its direction by modifying the hydraulic cylinders that press on the finished tunnel ring, as opposed to turning like a car. Typically, each cylinder pushes the machine forward with equal effort. The system only modifies that balance to steer. For instance, the cylinders on one side extend somewhat more than those on the other if the machine needs to turn slightly to the left. Surprisingly, during a single advance, the difference is frequently only a few millimeters. Additionally, the cutting head itself is crucial. The machine's front part may pivot slightly in relation to the rest of the TBM thanks to its articulation joint. Because of its adaptability, it is feasible to handle mild curves without overtaxing the machine or causing damage to the freshly laid concrete liner. A tunnel boring machine isn't just a giant drill. It's a complete underground construction plant that digs the ground, takes out the spoil, puts in the tunnel lining, and steers with incredible precision, all while keeping the city above safe. If you like this deep look at how tunnel boring machines work, remember to hit the like button on the video and subscribe to the channel for more 3D engineering explainers. Thanks for watching. See you in the next video.